All right, so in this video, we're going to be talking about similarity transformations and the specific kind of similarity transformation that can diagonalize some matrices. Now, a similarity transformation satisfies the definition that a matrix can be created from multiplying a transformation matrix P times another matrix times the inverse of P. And therefore, if it satisfies this definition or the definition where A is that same similarity transformation inverse times our T matrix times our similarity transformation, if either of these definitions are true, then A and T are said to be similar matrices. Now, there are some common properties of similar matrices in that similar matrices have the same determinant as each other. So det A is equal to det P or det T. So the two matrices, and you can see that if you go through using the matrix property of determinants for multiplication, that the determinants of P inverse and P are going to cancel each other out because they're reciprocals of each other. And so this will hold. Any similar matrix is has the same determinant as the matrix that it is similar to. Now, the ones that are the most important to us in this context are the ones that allow us to create a diagonal matrix. So for example, where A is equal to P inverse D times P, where D is a diagonal matrix and P, it turns out, is created based on the eigenvalues and eigenvectors of the A matrix. So what we're going to do is we're going to do an example here to look at a matrix A, which is not diagonal, and we're going to show that it can be diagonalized and find the similarity transformation that makes that work. So our theorem basically says that D is diagonalizable if it has one eigenvector for every 0 of its characteristic polynomial up to and including multiplicities. So another way of saying this is that the eigenspace of eigenvectors for the matrix A, which is n by n, spans Rn. So if there are n eigenvalues, again, including multiplicities, then if there are n eigenvalues to go with them, then we can diagonalize the matrix and we can span all of Rn with those eigenvectors. Now, the eigenvectors must be linearly independent if they're for the same eigenvalue. If they are from different eigenvalues, they're already linearly independent. So we really only worry about the ones where there is a multiplicity for the eigenvalue. If there are multiplicities for an eigenvalue, sometimes you will get a full complement of eigenvectors that satisfy the multiplicity, and sometimes you won't. So there are also other theorems that relate to this that suggest that if you have distinct eigenvalues, then this is guaranteed. Distinct real eigenvalues, then diagonalization is always possible because you have to have a minimum of one eigenvector per eigenvalue. If you do have multiplicities, then sometimes it will be diagonalizable and sometimes it won't be. And so we would want to check to see if we have the required number of eigenvectors for each of the multiplied eigenvalues. But as long as we have the right number of eigenvectors, then we can do this. So we're going to look at a 2x2 case just to illustrate the general process. You can replicate this, of course, in higher dimensions, but of course it takes quite a bit more work. So let's start with our A matrix that we're going to work on. And our A matrix is going to be 4, -1, 2, 1. And so we're going to start by finding our characteristic polynomial. So A minus lambda I is going to be 4 minus lambda, -1, and 2, and 1 minus lambda. And so the determinant is going to be 4 minus lambda times 1 minus lambda plus 2. And if we multiply everything out, we're going to get lambda squared minus 5 lambda plus 4 plus 2 is equal to 0, or lambda squared minus 5 lambda plus 6 equals 0. And so when we factor that, we're going to get lambda minus 3 and lambda minus 2 is equal to 0. And so lambda equals 2 and 3. And so now we need to find the eigenvectors that go with each one of these. So for lambda equal 2, let's start there. So we'll have 4 minus 2 is going to be 2, and -1, and 2, and 1 minus 2 is going to be -1. So we can see this is clearly dependent. So our equation is going to be 2x1 minus x2 is equal to 0 for our homogeneous solution, and therefore 2x1 equals x2, and x2 equals x2. Or we could rewrite this as x1 is 1/2 x2. And so that's going to give us v1 for lambda equals 2 is going to be 1 and 2. So if I let x2 equal to 2, then x1 will equal 1. And then we repeat this process for lambda equals 3. And if we put that into our A minus lambda I matrix, we have 4 minus 3 is equal to 1. And if I put that into the bottom row, I get 1 minus 3 is going to be -2. Again, we can see that they are independent, or that they're dependent. And so our top equation is this, and that's going to give us x1 is equal to x2, and x2 is free. And therefore, our second eigenvector is going to be 1, 1. Fantastic. So now that we have our two eigenvalues, then our similarity transformation is either going to be one, 2, 1, 1, or its inverse. And we'll double check to see which one it is. So I should also specify the diagonal matrix. Should be the diagonal entries in the same order as the original eigenvectors in the matrix, the transformation matrix. So that would be 2, 0, 0, 3. And then let's find out what is PDP inverse. So P D and then P inverse we can calculate by using our two-dimensional inverse formula. That's going to be 1 minus 2 is going to be 1/2. It's going to be 1 minus 2 is going to be -1. And then we're going to put in our 2 by 2 inverse. We flip the order of those, and then we change the sign of the other ones. And if we distribute that -1 through the matrix, then this will be this, and that, and that, and this. And then if we do our multiplication, let's see what happens. So if I multiply the first two together, I'm going to get 1 times 2 plus 1 times 0 is going to give me 2. And then over here, I'm going to multiply with the second column. So 0 and 3. And then multiply here, I'm going to get 4 and 0. And then over here, I'm going to get 2 and 3. And then I'm going to multiply by that one. And if I multiply by that one, I'm going to get -2 and 6 is going to give me 4 and 2 and -3 is going to give me -1 and 4 and -1 is going to give me -4 and 6 is going to give me 2 and 4 minus 3 is going to give me 1, which is my original A matrix. And so if I want to take A and turn it into the diagonal matrix, then I can do that by, again, flipping the order of multiplication and multiplying the P inverse in front times A times P on the other side, and that will turn it into the diagonal matrix.